Well, it's a great pleasure to be here. I'm of the Pink Floyd generation. So I was actually there when the classical computer stack was built, and I thought I'll just give you a few comments of how that worked out, which so far has gone pretty well, and what lessons we can learn from watching how a completely new technology, well, actually a whole set of technologies, crystallizes into a major sector of our economy. So I thought I'd put an agenda together which starts with my dogma for information processing. I've been in the computer architecture business for a long time, and over years you realize what really matters and what are sort of secondary issues. And the core issue is this what I call the dogma of information processing. Then our view of the three phases of quantum computing. Then I'll spend a bit of time comparing the classical computer stack, which grew up over many years, with the quantum computer stack that is being created at the moment. And then Carmen asked me about my expectations of the scale-up of the quantum computer sector over the years. And then, of course, I'll finish off with the networking bit and the data centers. So let us start off with the dogma of information processing. I think the very most basic thing that you've got to get right if you do any information processing is to find the right balance between computing and communications. I didn't realize how fundamental that was until I looked at all the different things that I've done in my life, because I've been involved in producing computers with the BBC Micro, producing a microprocessor, the ARM, which is the processor in your mobile phone, and now I'm pleased to tell you also the processor that is replacing Intel in the data center. And I will come on to why this is that a little processor from a minor computer company in the UK has become the number one processor in the world at selling the Intel architecture 20-1. So if you look at the numbers of microprocessors sold in the world, it is dominated by ARM with a 5% market share to a company called Intel. So what happened in the classical computer stack is that the von Neumann, so-called von Neumann architecture became dominant. All the processors that we have at the moment, be they CPUs or GPUs, are von Neumann architectures which separate the memory from the computing. And this balance between computing and communication is particularly apparent because the main problem really in a von Neumann architecture is if you have the memory here and the processor here, you spend all your time thinking about how you can get the data from the memory into the processor, do a bit of processing, and then write it back. That's also where all the energy goes. So it's actually a bloody stupid way of doing computing, but it's the only way we found out how to do this at scale. And therefore, very interestingly, there is a completely new type of architecture, which is informed from, of course, our own brain. That's why it's called neuromorphic, which does not move the data at all. It leaves the data where it is and does in-memory computers, it's called, which is exactly what's happening. In the brain, of course, the neurons are both storage elements and processing elements. And if you do that, interestingly, you can reduce the power consumption by 2 orders of magnitude. So this is not a small change. This is a big deal. The problem with doing in-memory compute, which clearly is the next compute architecture that we're working on. I've made 4 investments in these companies already. The problem with this approach, attractive as it is, low power as it is that we've perfected the memory storage in DRAMs to such an extent that in a single DRAM you can now store a megabyte of information. If you now do in-memory compute, of course, your density goes to hell. So this only works for AI on the edge. On the other hand, there's also a big shift in the industry for trying to move the load out of the data center towards the edge. So if you have small things on the edge that do a lot of the pre-processing, that's actually a good thing. It saves power, both on the processing, if you have a neuromorphic chip on the edge. It saves a lot of power there, but then it also saves a lot of power in transmitting the information back to the data center. So, you know, people normally talk about quantum computing as being the next big thing. Very few people realize that actually the right architecture for AI in particular is not CPUs or GPUs, it's actually in memory compute. So we have a big change in the main architecture in classical computing happening as well. Now, if you look at, back to the existing von Neumann architectures, the whole balance between computing and communication has to do with the memory hierarchy. So how do you stage the memory out of the main memory? That's why we have caches. The computer departments of the world are filled with PhD theses on cache replacement algorithms. This is a big deal. If you put the right information close to the processor that it uses all the time, you can save energy, you can increase the speed of it because the local memory, of course, is much faster than fetching. So one of the key problems throughout the early classical computing was to optimize this access to memory and therefore get the right balance between computing and communication. Of course, a very elegant balance is not to move the data at all. That's why in-memory computers are good. Now we get an enormous amount of help in quantum computing from the spooky action at a distance, or the spukhafte Fernwirkung, as we say in German, which is what Einstein called it in his original letter to Max Born. So interestingly, entanglement, gives us a real leg up when it comes to doing a computing across chips, which is not available to classical computing, of course. And the sort of enabling building block for that, of course, is the teleported CNOT gate, which allows you to do processing across a number of chips or computers using entanglement plus classical communications. So the other thing that I can tell you about in terms of how classical computing grew up over many years is there was a company, still is a company called IBM that took the sand off the beaches. It made the ingots. It then built the chips, which it put on circuit boards, which it put into computers. Then it wrote the operating system and the applications, and it serviced it and sold the computer to you. And at the end of the life, it would take the computers away from you again and send you a new one. So it was totally vertically integrated. And in many ways, the history of classical computing is sometimes called horizontalization of the industry, because these layers appeared, different layers. There were some people that specialized on ingots and on these wafers. And then IBM said, well, we don't really, this is not the main contribution that we make to the business, so let another business do this. So if you look at that, all the different stages of this classical computer stack, it all now has separate sectors that have become, with many companies in them that provide solutions for that layer. And the reason why I'm mentioning this to you, because is this horizontalization, these layers that are appearing, that appeared in the classical computer stack, are beginning to crystallize out in the quantum computer space, but they're not quite the same. But let me tell you the experience from ARM, really, was this appearance of the GDS2 tape. So Jeremy Saunders, the founder of AMD, famously said, "Real men have fabs." What he meant is that if you produce a chip, if you design a chip, you really have to have a fab that then produces that chip. So the relationship between the design and the actual implementation of the chip in a fabrication was so tight that if you designed a computer, it would only work on one manufacturing plant. And then this GDS2 tape appeared where you could specify your design, typically in sort of triangles and rectangles. So it was a geometric standard. You could hand that GDS2 tape to any CMOS fab, and they will give you a working chip back. This was a really rather fundamental event in classical computing, because all of a sudden it enabled chip companies to appear that didn't have fabs. They were all called fabless chip companies. And ARM started as a fabless chip company because we didn't have the money to produce a chip company. In fact, I always say that one of the great advantages that I gave the ARM design team is that they didn't have any money, and therefore they couldn't make a very complex processor. And that is one of the reasons why it's so low power, because they just didn't have enough money or people. It's the only processor that was produced by two people, albeit two geniuses. So ARM first appeared as a chipless company, as a fabless company, but then it became the first chipless company. So ARM actually doesn't sell chips anymore. We used to start off with, but we now just license everybody, basically. There is not a single semiconductor company in the world that doesn't have an ARM license. And we produce, just to give you these amazing statistics that I still can't believe, we produce 30 billion ARMs every year. So given that there are only 9 billion people on Earth, on average, everybody on Earth gets an extra 3 ARMs to the 30 that they have already. So you might well ask, well, where are my 30? And the answer is in your mobile phone, because some of you might know that the ARM is the application processor in the mobile phone, but very few people know is that there is an ARM in the USB, an ARM in the Wi-Fi, an ARM in the Bluetooth, an ARM in the touch controller. So every phone typically has sort of 20 ARMs, and so does every PC. So coming on to quantum computing, some of us feel that there are 3 main phases that quantum computing is going to go through. The NISQ era that we've just left behind was all about producing physical qubits. And we've arrived at about 1,000. Then the next phase, which has just started, and Quera was really the company that introduced logical qubits, which are error-corrected qubits, and we've got about 50 now, is the second one. But if you want to have a fault-tolerant scale quantum computers, you really need distributed quantum computing, but that needs a networking connection. So that's the 3. And the key the key parameter might well be entangling. So it's the entangling rate that allows us to do this. Now, one of the big questions, if you believe in these 3 phases of quantum computing, is which of the different things that we're developing in quantum computing will be sectors that are different layers, where the layers are so different that it actually warrants to have separate companies for it. And my test for whether this will happen or not is actually the quality of the layers, both at the bottom of the company and at the top. So at the bottom, the inputs, can you buy the things that you need to buy for your business in a clean specification. But in a way, more importantly, is the top clean interface. Can you create a layer at the top for your customers that is interesting to a number of different customers, not just one? And can you set some sort of standard? So if we go through classical versus, you of course know about a bit and a qubit, and these qubits have these superposition and entanglement properties that don't exist in classical computers. And then if you look at the actual implementation and the representation of bits in classical hardware, we got a phenomenal gift from nature with semiconductors. I mean, we totally lucked out with semiconductors that they exist, because if you look at how we started in computing with mechanical devices that are very unreliable and they don't scale, so that was no good, and they're slow. You know, they had to crank these mechanical devices. Then valves came. They were fast. You know, you could clock them at a reasonable speed, but they were terribly unreliable. And they wouldn't scale either, because you couldn't make valves small enough. And then semiconductors came along, and they really had all the desired properties. They were fast, you know, into the gigahertz region. They were reliable, and we'll come on to this in a moment. They're incredibly reliable now, and they scale. So silicon transistors, and this is another historic fact, since I lived through it, which might be relevant when to the different modalities that we have for qubits at the moment. I remember these fights between NMOS and PMOS. So people, you know, there was the PMOS camp and the NMOS camp. These are positively doped and negatively doped semiconductors, and you know, they just really thought that they were going to win. And then there was this odd thing called CMOS, which was far too complicated. Nobody believed that they would ever get anywhere. And yet it was CMOS that won out, partially because of the low power. It's always been a low power switching device. So when we come to you know, the quantum part of the stack, we've got superconducting and ion qubits at the moment that you know, have the nose out front. Then the neutral atoms came left field and overtook them in many ways. They were the first ones to show logical qubits. And then in the back, there are people who think that photons are the really long-term solution. And you've got a big advantage with photons, that they, you know, they've been coherent. Some of them have been coherent for 13.8 billion years. So, you know, they really have a good approach to coherence. But then there is another lot of quantum computer companies that believe that really the only way you can win is by piggybacking on the enormous development and investment that we've made in silicon. Silicon is one of the best understood materials. You know, the amount of research that has gone into processing silicon is, I think, unprecedented. We've never put so much money into developing a material in silicon. And then there are, you know, outliers like the Majorana topological computers from Microsoft. There are NAND gates, of course, that are universal in classical computer, and the universal gates in quantum computers, which is a little more complicated. And then we've got a thing called a microprocessor here, which is actually pretty handy, because it's a single circuit that is a Turing machine. So anything that you can calculate, you'll be able to calculate with a processor. Now, this is a little more obscure on the quantum side. We don't really have a quantum microprocessor yet. We have a sort of a set of quantum circuits in our library of quantum circuits that do things. So there is still development work to be done. And then, of course, come the quantum networks, which are enabling this. Now, on the software side, there is a fantastic stack on the classical side, and I would just want to point out error correction, because these transistors that we're building in the classical stack are incredibly good now. They're sort of 10 to the 15, which means that you can run billions of these transistors at a gigahertz rate for years, and you don't get an error. We've also dealt with memory errors in quite an elegant way. You only have about a 20% overhead to error correct memory and make them really very, very usable. And this has become a mega problem in quantum computing. Error correction is 5 minutes. Yep. Error correction is, is a mega problem. And because it is so big and so difficult, you know, one of the things that is very exciting is that this might become one of the separate layers. You know, it is expected now that this will be a layer for different companies. And I think the same thing is true for networking. So if you look at the scale-up, the Apple M3 now is the largest processor with about 200 billion transistors. We've got 2 terabytes of NAND gate from microns, and we're down to 3 nanometers. And in the data center, we're going up to terabits per second. And you know the WAN, and there are good standards. All this is incipient still in the quantum computer space, where we're only about 100 physical qubits, 50 logical qubits. And one of the interesting new targets that has appeared, especially in the UK, is a megaquop by 2028. You know, given that we run, you know, at gigahertz and the classical thing, this is way behind. And we've got quantum networks that are now up to 250 kilometers, and as a real repeater challenge. LANs and WANs have become part of our networking infrastructure, and there is this interesting fight between QKD and post-quantum on the security standard, which I can give a separate talk on. And of course, the real aim is to have distributed quantum computing which multiplies the power of computers by linking them together. In the background here, I've chosen the largest data center in the world, which is Hohan in Inner Mongolia from China Mobile. And Meta is planning the largest data center so far with 1 million GPUs. Every GPU, of course, has 36 ARMs associated with it, so there's 50 million ARMs, consuming 2 gigawatts. And then there is this huge Stargate initiative of $500 billion in the States. And therefore, power has become one of the leading issues. Again, a great advantage for quantum computing, because a quantum computer typically runs at a kilowatt, and a supercomputer uses megawatts. And in some applications, of course, a quantum computer is faster than a C computer. And we know that P is greater than BQP, so we know that quantum computers can do things that classical computers cannot do. So in conclusion, we know that quantum computers work, and so do quantum networks. There was doubt about that just a few years ago, whether they will ever work, but we now know they work. The development is actually speeding up. Of course, the classical computer stack is far ahead of the quantum one, but the quantum one is developing super fast. And I leave you with the thought that maybe one of the key parameters to watch out for is actually the entangling rate of multiple computers. Thank you very much.